Okay, so here we go. This is where, right before this is where we left off last time. So we talked a lot about linear transformations. We defined various objects related to linear transformations. We did some examples, etc. So a little bit more laying of groundwork. So we need to, there's a neat theorem here that relates the kernel of a linear transformation and the image of a linear transformation. Now, this is a special linear transformation, not just any linear transformation. We need for the domain to be a finite dimensional vector space. So that's non-negotiable. That's got to be there. So anyway, but that being said, for such linear transformations, there's an amazing fact that the dimension of the kernel, the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain. What's surprising about this theorem is that the kernel and the image don't even live in the same world, right? The kernel lives inside of the domain. The image doesn't. The image lives inside of the target. So these two vector spaces, these two subspaces, live in different worlds, and yet they obey this strong relationship between their dimensions. So really powerful fact. I'm going to show you how to prove this fact. I am going to actually do all but a proof of this fact. There is one little sticky wicket that I'm going to assume for the moment, and then I'll fill in the blanks after spring break. And it just turns out it's a much nicer proof if you make this one little assumption that we're about to make here and then fill in the blank later. If I don't make this one little assumption, then we in some sense have to redo a bunch of work that we've actually already done. And so anyway, I think y'all will like this compared to what the book does. So the one little assumption, I'm going to highlight this in red. The thing that I'm going to defer to later, now I owe you an explanation of this fact, that'll come later, is that actually every linear transformation on a finite dimensional domain can be written as a matrix. Like I say, some work has to be done to establish this, but this is a true fact. If you've got a linear transformation on a finite dimensional domain, it can be written as a matrix in a certain way. Okay, so let's assume that, and with that in mind, good news. We are looking at this kind of a linear transformation. We are literally looking at a matrix, right? This isn't just some linear transformation. We've got a matrix. And for matrices, we already know that the kernel is the null space of the matrix. We already know that the image is the column space of the matrix. Right? And we already know that the dimension of the null space plus the dimension of the column space is equal to n, namely, you'll notice here, the dimension of the domain. So we already know the thing that we're trying to prove. We already know it in the case of matrices. And as we will see soon, all of these linear transformations are matrices. So thus the proof, right? So it's a really easy argument. Basically, it's a, by the way, side note, we realize that we've already proved this. Okay. Just for your own curiosity, take a look at how the book proves this. They don't make the little assumption that I make, again, with promises to fill it in later. And so they have to do a bunch of work. So anyway, I think you'll like this better. Alrighty. There is a corollary to this theorem that we need to talk about. This corollary talks about linear transformation that has the additional feature of being what we call bijective. Now, y'all probably have not heard that word before. You may have heard the words one-to-one and onto. A function that is bijective is simply both of those, one-to-one and onto. If you don't remember one-to-one and onto, the context where you might have / should have seen it before would be a single variable calculus class where you talk about inverting functions, and in order to invert a function, the function has to be invertible, and in order to be invertible, you need to be 1-to-1 and onto. So anyway, if your single variable calculus course didn't go through that, don't worry about it. All we're going to talk about is the pair of the both of them, namely a function being bijective. Yeah, question?
Is 1-to-1 and onto equivalent to like injective and surjective?
Yeah, 1-to-1 means injective and onto means surjective. Yeah, that's other words that apparently I guess we must have heard. Yeah, absolutely. Right. Okay, so I'm going to talk about a bijective. Don't forget linear transformation. And here's the idea of bijective. A bijective function is what I like to call a perfect pairing. So it's a buddy system kind of a deal. So you've got a domain, you got a target, right? The input world that things that go into the function come from. The output world that things that come out of the function go to. Perfect pairing means that they pair up like this. For every output, there's exactly one input that goes to it. Exactly one, no more, no less. So if that happens, which does very often, we have a bijective linear transformation. So what the theorem says is that if you have a linear transformation that is bijective, then the punchline is that the domain and the target have the same dimension. And this ends up being a powerful result. We're going to see a huge application of this on the next page. Let me prove why this is. Like I say, it's a corollary of this fact up here. Let me walk you through the details there. I'm going to draw sort of a figurative picture of such a function, domain, target. Obviously, vector spaces don't look like this, but just to communicate kind of the gist and all I really need to communicate, this is going to end up being good enough. So keep in mind we have 0 vector in the domain. We have a 0 vector in the target. Right. We've got some function. And now remember, we're assuming that our function is bijective. Bijective means, again, perfect pairing. For every output, there is exactly one corresponding input that lands on it. And so, for example, maybe it looks something like this. Notice that every output vector here is hit by exactly one input vector. Okay, so now let's take this theorem. We already know this theorem is true. Dimension of the kernel plus the dimension of the image.
Did you start recording?
Did I not hit the recording button? Oh gosh, really? I thought I did. Could have sworn I did. Where is the? I'm going. Okay. Yeah. But I appreciate the reminder. No, I appreciate the reminder because I will forget at some point. I'm sure of it. Right. So So we already know that this theorem is true. Dimension of the kernel plus the dimension of the image is the dimension of the domain. Let's see how does that apply in this scenario. What is the kernel? Well, the kernel is the collection of vectors over here that land on the 0 vector. Well, this is a bijection, right? This is a perfect pairing. So it's just the 0 vector that lands on the 0 vector in this perfect pairing linear transformation. Okay, so what is the dimension of a subspace consisting of just the 0 vector? Well, it doesn't have even so much as one dimension to it. It is 0 dimensional. So the dimension of this kernel is 0. Okay. Now let's look at the other side. What is the image of this linear transformation? Image is the collection of all actual outputs. Again, we typically distinguish between the image and the target. The target is the world that the outputs have to land in. The image is what actually comes out of here, right? Well, again, this is a perfect pairing. Perfect pairing means that everything in the target gets hit by some point in the domain. So actually the image is the whole target. The image is W, right, in this scenario. So in this scenario, 0, of course, goes away, and you see we have dimension of V equals dimension of W, dimension of the domain equals dimension of the target, and we have our result that we posed down here. Okay, so I'm going to show you how this theorem ends up being super powerful. We're going to close a loophole, a dangling thread we're going to cut finally. Pick your metaphor. From Chapter 4. Let me remind you, from Chapter 4, we talked about differential equations, linear differential equations. Specifically, we talked about solutions to homogeneous, nth order differential equations satisfying the conditions of the existence and uniqueness theorem. And our big theorem, one of our big, we had several, but one of the big theorems was that set of solutions was n-dimensional. We didn't prove that. Right? We proved it was a subspace of Cn, and we asserted that it was n-dimensional. We used that it was n-dimensional, right? But we never actually got around to establishing or proving that it was n-dimensional. So here's where we're going to prove it. By the way, now why did I not prove it then? Well, because it would have been super inconvenient, and we didn't have the powerful tools that we have now, and it's going to end up actually being really very straightforward now that we have the tools from the previous page. This powerful construction of linear transformations. So here's how that clever argument works. First observation. The set of solutions is a vector space. Old news. We established this before. It's a subspace of Cn. One of the first things that we proved back in Chapter 4. Okay. Next observation. Now this one's a little bit silly seeming, but the set of initial values. Remember what an initial value is. An initial value is some choice for what is y of 0, y prime of 0, y double prime of 0, et cetera, all the way down to the n minus 1th derivative. We talked about why we call these initial values. We call them initial values because a prescription of what we're calling here initial values gives you an existence and uniqueness theorem, right? That with an initial value, there is exactly one solution to the differential equation. All right, so innocent observation. These initial values, if you just look at what they are an ordered list of n real numbers. They are a vector in Rn. Right? So in fact, there's another way to think about it. This set of initial values is Rn. That's one way you can think about it. Okay. All right. Now I'm going to define a linear transformation. We're setting up some machinery to make this all work. Linear transformation. My linear transformation goes from my vector space of solutions to my vector space of initial values. Now remember, there's lots of weird linear transformations that you can define. Not all linear transformations look like Euclidean input, Euclidean output formula that involves only linear terms, right? So there are linear transformations of various different sorts. This one kind of sort of looks like the formula for the Dirac delta function and the variance on the derivatives of the Dirac delta function. What it is if you give me a function, specifically if you give me a solution to the differential equation, the value of this linear transformation t is, well, whatever its corresponding initial values are. Whatever y's corresponding initial values are. Now that's weird, right? I mean, but it remains that, look, if you give me a y, I can plug in x equals 0 and compute y of 0. And I can compute y prime of 0, and you gave me the y, I can compute all these different things. So you give me this input, I give you this output. That's what t does. Okay. All right. Now, what a weird linear transformation. What are we going to do with this? First observation I'm going to make about it. actually, let me restate that. The first observation I'm going to make about it is that it is a linear transformation. I'm going to ask you all to check that. This is a good practice problem. Again, it's a lot like other practice problems that I gave you last time. It's a lot like the Dirac delta function. You can just confirm that if you put in a sum of two functions, its initial values are the sum of the individual initial values. And then likewise for scalar multiples. So make sure to check that, confirm that it's actually a linear transformation. Okay, that said, I claim this function t is bijective. I claim that it's a perfect pairing. I claim that for every output, there is exactly one corresponding input. Let's say that a little bit differently. For every outputs being initial values. Okay, so for every initial value, there is exactly one corresponding input, namely solution. Okay, so for every initial value, there is exactly one corresponding solution. Where have we heard that before? For every initial value, there is exactly one corresponding solution. That's our existence and uniqueness theorem from chapter 4. Right, our cornerstone basic theorem on which all the linear algebra rests. For every initial value problem, there is exactly one corresponding solution. Now, just to give you a visual aid, this page here, by the way, is not part of the great big PDF file of notes, but I think this is a nice little supplement. It's on the Sakai site for the course. And so if you want a copy of it, it's there, and you can just grab it. But here's just a visual. This is what solutions look like, right? Solutions that go into our linear transformation. They look like this. They're curves. They're y as a function of x. Here's what our target looks like, right? We're going to be looking at x equals 0 and looking at the the value and the derivative and the second derivative, all the various different calculus properties, you might say, of said function at that point. Okay. So again, the function is a no big deal function. The function just says, well, you give me a function, I can check out its initial values. That's all this is. And seeing the bijectiveness of this, again, is just really a restatement of the existence and uniqueness theorem. For every output, there's exactly one corresponding input. For every initial condition, there's exactly one corresponding solution function. Okay. All right, it's just a visual aid. So, knowing that this is one-to-one and onto, knowing that this is a bijection, we have a bijective, perfect pairing, in other words, linear transformation, and that immediately tells us the dimension of the domain is equal to the dimension of the target, and it's all over at this point. I mean, we're really pretty done. The dimension of the domain is equal to the dimension of the target. Here they are. The dimension of the domain, well, let me stick to my colors. My domain, this set of solutions, in other words, that I'm interested in, its dimension is the same as the dimension of the target, namely this set of initial values, namely Rn. So the dimension of S is equal to the dimension of Rn. That's N. So S is n-dimensional, as desired. It's a real slick proof. Very cool. Very, very tricky argument. Okay, I'm a big fan of this proof. Notice it uses some of our powerful ideas. That's nice. Also notice, if you don't do the proof this way, you've got a bunch of work ahead of you. Check out the book's argument in Chapter 4. They make the argument without the benefit of this powerful tool of linear transformations. After all, in Chapter 4, they hadn't developed the idea of linear transformations. They can't. Right? So they did the only thing they reasonably could in that position, which is prove it the old-fashioned way, which is to literally construct an explicit basis for the set of solutions. And oh my God, it's a lot of work. I encourage y'all to take a look at it. If you look at that proof, what you'll find is that they pretty much take a basis for their set of initial conditions, and they use that basis to create the basis for the set of solutions and use the independence and span of this basis to establish the independence and span of this basis. But there's a lot of details that goes into that. It's a bunch of work. It's a bunch of effort. Much easier to just cite this theorem, boom, done. Right? Much more powerful. Okay. Alrighty. Okay, so moving along now to section 5.2, new topic. We're going to talk about the algebra of linear transformations. Just want to let you know where this is going and why we're doing it. It turns out that linear transformations can be thought of as being elemental little objects on which you can define operations. We don't typically think of them that way, right? We think of linear transformations as being functions. We think of, vectors as being elemental objects that you can add and scalar multiply and stuff like that. But we think of linear transformations are functions between, a world of elemental objects to a different world of elemental objects. But I want to think of the linear transformations themselves as being little elemental objects and establishing operations between these elemental objects. And it turns out that what we're going to be able to do with this is prove a bunch of other results that have been loose threads that we've had dangling since chapter 4. Just to let you know what they are. Y'all remember in chapter 4 we said that if you have a characteristic polynomial, you have a root, and if it's got a multiplicity, then you take your exponential solution and you just start multiplying by x. Remember that whole business? You just multiply by x a bunch of times? I never proved that. I just asserted that was true. I confirmed it in one case. And I just said, by the way, this always works. Never proved it. So I owe you all a proof of that. And the proof is going to involve using the algebra of linear transformation. Section 4.3. I just made this assertion. There's this theorem, right? The big theorem in section 4.3. The how do you guess correctly theorem from 4.3. I just asserted that if you have a unfortunate coincidence, your magic number, root of the characteristic polynomial, just multiply by x to the m and it all works out. Never proved that. I gave you kind of a sanity check, right? A vague, super weak plausibility argument. At least I gave you an argument that showed that it wasn't implausible, right? I don't even know if I call it a plausibility argument, but we certainly never proved it. And using the algebra of linear transformations, we're going to be able to prove that theorem in broad strokes. I'm going to leave out the details. Okay, so we've got to set up some work here, and bear with me. We do have to define a bunch of stuff, and ultimately no big deal. If I want to think of linear transformations as being elemental, sort of atomic little objects that I can do operations between, I got to write down what those operations are. The first couple of them are really no big deal. How do you add linear transformations? Well, linear transformations are functions. We already know how to add functions. If I want to multiply a linear transformation times a scalar, how do I do that? Well, again, linear transformations are functions, and we already know a formula for how to multiply scalars times functions. Okay, so we already have, in some sense, an addition part of our algebra, a scalar multiplication part of our algebra, right? What we don't have, and what we can't sort of, rip off from previous work, you might say, what we don't have is a formula for how to multiply linear transformations. That's going to seem like a weird choice that I'm going to make down here. I'm going to pull this out of thin air. If you have two linear transformations, the product of those two linear transformations is going to be defined by the composition. And don't forget, the way you compose two functions. It's just like in single variable calculus. Like from the chain rule. Y'all remember the chain rule. Composition of two functions. Well, you take what comes out of the one function and you put it in to the other function. That's it. So weird to think that this would work, but we're going to use compositions as our definition of multiplication. Very strange. Now a pretty good question that comes up at this point is, look, you can define whatever you want. It's a free country, right? But if I make this choice to define with compositions, why would I call that a multiplication? Right? I mean, you can see up here in this picture, I mean, it's reasonable that I would call this an addition because, well, it comes from an addition. That seems plausible. Why would I call this a scalar multiplication? Well, because it comes from a scalar multiplication. That all tracks pretty well, right? But in what sense are compositions products? Right? We have no good motivation there. The answer to this question, why I'm going to call this a product, comes on the next page. I'm going to call it a product because if you write down the properties that these operations satisfy, right? And by the way, let's take a moment to recognize, isn't all that familiar? That all looks like high school algebra, right? The punchline is, this thing that I have called a product behaves like a product, algebraically. In terms of the rules, it just does. It's got an associativity, like products do. It has a distributivity with our existing addition, just like products do, right? It behaves like a product. So be it, right? It seems like a reasonable thing to call it. One little bit of bad news. It's not commutative. Multiplication of linear transformations is not commutative. I'm going to file this, though, as not shocking. If you think about it, compositions in general are not commutative. Sine of e to the x is not the same as e to the sine x. So we don't really have any reason to believe why it would be commutative. It's disappointing. Products that we've seen in the past have been commutative. But honestly, not even all of them. I mean, don't forget, matrix multiplication is not commutative. Right? We know AB is not equal to BA. So we've seen non-commutative products before. So this one, not our first time. Okay. All right. Now, these properties all deserve to be proved. I'm not going to prove all of them. I'm going to leave these as exercises. I do not expect you to prove all of them. I'm going to show you how to prove one of them. I would like for y'all to do, one, maybe two. Do them until you are quite clear that you totally see, no question about it, exactly how to do these, and observe that they're all kind of the same, right? But make sure you're comfortable with they're all being kind of the same, and then don't do the rest of them, right? But I should do at least one. Here's the one I'm going to do. I'm going to prove property number 8 here, that that's equal to that. Proof's over here on the next page. I'm going to prove that this function is equal to that function. Now, how do you prove that functions are equal to each other? You prove functions are equal to each other by showing that no matter what you plug into both of them, you always get the same thing out from both of them. Right? I mean, this has got to work, right? If you have two functions such that no matter what you plug in, you always get the same thing out of both functions, those are the same functions. Yeah? So, here we go. We just got to plug in. I need to compute this thing, see what we get. I need to compute this thing, see what we get, and make sure that they are indeed the same. Now, how are we going to compute this? We're just going to follow the rules. You go a couple pages back here, and we have rules for here's how you multiply. Multiplies are compositions. So I'm just going to follow that rule. Here's how you add. You want to add two functions, you add their output values. I'm just going to literally follow the rules, and the result will follow immediately. So here we go. Notice we have here a product. That times that. We multiply by composing. Notice I'm first plugging into T, and whatever comes out of there, I'm going to plug into R plus S. Straight up composing. Okay, now notice we have an addition. I have R, to which I'm adding S. How do I add R and S? Well, I add their output values, right? This addition of linear transformations is executed by this addition of their output values. And notice literally I'm just adding the output values of R and S, plugging this into each of them. It's following the rules. Everybody happy? Okay. Same thing for this down here. Here I have a sum. I add two functions by adding their output values, following the rules. And then for how do I multiply? Well, you multiply by composing. And again, these are the two functions that I am multiplying, and so plug into one, and whatever comes out, you plug into the other. And likewise for the other term. Yeah.
Are linear transformations
Are
linear?
what now?
Are linear transformations linear?
I mean, by definition, yeah. Even though that's as functions, yeah. I mean, one of the requirements to be a linear transformation is as a function, linear combination of its inputs gives rise to a linear combination of its outputs. Here, though, we're not thinking of them as functions. We're going to kind of step away from thinking of them as being functions and think of them, again, as kind of little atomic, little elemental little things that I'm defining operations on. But yes, all linear transformations and all results of operations. So, for example, when you multiply two linear transformations, this composition also linear. Yeah, absolutely. Yep. Okay. All right. Okay, so we get the same thing out from both sides. Therefore, these are the same functions. Okay, so we've created an algebra. We've got all the tools that we need to be able to manipulate these things. We have an algebra of linear transformations. We can add, right? We can scalar multiply, and we can, multiply. Three operations that we have that we can apply to linear transformations. Okay, now, having established this algebra, I need to build up some very specific machinery. I've promised y'all that we're going to prove some results. We're going to prove some old claims that, dangling threads. In order to do that, I need to build up some tools specific to those applications. I'll remind you, for our first two, that's a linear transformation. We talked about it previously. I want to say it was Monday, I think it was. So not hard to check. Proved in the notes that this is a linear transformation. Here's another one. Now, I don't think this one's in the notes, but this is an easy check. Make sure you can check it. This would be a good practice problem. I know I've given y'all a lot of practice problems. But there's a linear transformation that's defined by, given a certain function g, the action of this linear transformation is to multiply by that function g. So in the same way that d is the action of differentiation, in the same way, this thing, tg, is the action of multiplication by g. And this is linear. If you were to do the action of multiplication by g on a linear combination of f's, C1 F1 plus C2 F2, you get easily checked the expected linear combination of individual outputs. So make sure you can do those details. We have here two linear transformations. Turns out these are a powerful pair of linear transformations. I make first a seemingly innocent observation, but going back to chapter 4, remember we looked at differential equations like this. Remember that we looked at this whole great, big, monstrous left-hand side, and we just called it L of y. We said, look, that's a lot to write down. This is unwieldy. I'm going to think of this as, look, there is a process. This describes a process of stuff I do to y, whatever y might happen to be, right? So stuff I do, I'm going to call L. This is the stuff I do to y. And we proved that L was linear, so this is also a linear transformation. The interesting observation I want to make, though, is that I can rewrite L itself, not L of y, but L itself, in terms of these other linear transformations up above. This is a new idea. This is a weirdly new idea. Up to now, L, again, let me just remind you, L has been, it's just been a placeholder. It's been a name that I kind of stamp on all this junk that I do to y. Right? I have not been able to look inside of L. Think of L as being made up of more elemental things. Break it up into little pieces. See algebra inside of L. Not at all. Look, L is L. L is all of that. End of story. Nothing else you can do with it. But it is. Look, it is this combination of those linear transformations at the top of the page there. And let me just, for example, let's look at this term right here. What does that do to y? What does t qn d to the n, what does that do to y? Well, just following the rules, d to the n says take n derivatives. T q to the n says multiply by q to the n. And notice we get, as promised, exactly this. Right? Likewise for all the other terms. Right? So this little formula here that I've got in green, this little formula involving algebra of linear transformations combining these T and D linear transformations, this algebra of linear transformation is what L is made up out of. And now we have the opportunity to study L in greater detail. Again, if you want to study something, you pull it apart and see what's inside of it. Take it apart, right? We can now take it apart. It's a huge, huge observation. Okay, a little bit of notation. If I had not written this with the T's, if I had just said Qn d to the n, notice what we would have written down. Well, we would have, look, this thing, it'd still be computed. That's what we would assume that was meant, right? So, in other words, the action of multiplication by G, that's what multiplication by G means. How about we just write it like that instead? Reasonable question, why didn't I do this in the first place? I wanted to, per the book's suggestion, emphasize that this action of multiplication by a function G is a linear transformation. I wanted to just be bluntly clear that it is in fact a linear transformation. I can treat it with the algebra of linear transformations because after all, it is. But now that that's established and sort of served its purpose, I'm going to rewrite things kind of this way. It's just a little bit easier. So along those lines, instead of writing it this way, I'm going to write it that way. Okay. We doing okay? Everybody on board? All right. Okay. Okay. So. All right. Now, here's where it's going to get a little bit weird, which I like to say because I know it's already gotten pretty weird, but it's going to get weirder. This statement here, if you have a constant coefficient, L, which good news. That's most of what we did in Chapter 4, constant coefficient L's. I'm going to make the ridiculous seeming observation that L is equal to P of D. And let me point out what seems most ridiculous about this statement. It's this formula right here, P of D. Can you do that? Is this garbage? Can you actually plug in something like a linear transformation into a polynomial? We've never done that before, right? The only things we've ever plugged into polynomials are numbers. You could talk about P of 1, P of 2 plus 7i, P of R, where R is some value, some complex number, P of Z. But we have never said P of bicycle. It doesn't make any sense. That's crazy talk. Meaningless garbage nonsense, right? And likewise, it seems equally nonsensical to say P of linear transformation. Doesn't it? Certainly it seems nonsensical. It seemed nonsensical to me the first time I saw this. Now, let me try to persuade you that this is not garbage. I want to remind you what P is. We've got a formula for P. I'll squeeze it in over here. P of lambda is a n lambda to the n plus, and then a bunch of terms that look like that, and then a1 lambda plus a0. Right, there's our formula for P. And notice, while we have only ever plugged in numbers into this, in fact, all this says is, whatever you plug in, you'd better be able to multiply it by itself several times. You'd better be able to multiply that by a scalar, and you'd better be able to take whatever you get and add to things of the same sort. So anything, I don't even care what. If you can multiply it by itself several times and multiply by scalars and add, cool, go ahead and plug it into the polynomial. It makes perfect sense. It's fine. Right? Nothing wrong with that at all. Why can't I plug a bicycle into a polynomial? Because I don't know how to multiply bicycle times bicycle. That's the problem. Right? But can I plug in a linear transformation? Sure. At this point, we know how to multiply linear transformations. We know how to multiply linear transformations times scalars. We know how to add linear. We've got everything we need. Everything we need to be able to do this. Cool. So, weird though this looks, this is not nonsensical garbage. That is, crazy idea to want to plug that into there, but it's not garbage. Okay. Now, next question. Is it actually equal to L? So we gotta check it, right? We gotta actually write this all down. First, let me write down what L is. Keep in mind, we wrote that down up here. We're now doing constant coefficient though, so these coefficients are now A's. And so we have a(n) d to the n, etc., a1d plus a0. That's what L is. Let's write down what P of D is. Here's our formula for P. P of D is what I get when I plug in D in for lambda. Right? So P of D, weird though it may seem, here it is. It is a(n) d to the n plus, etc., plus a1d plus a0. And sure enough, these two things are equal. Highlighter. So now, like I said, it's super weird, right? I mean, I get that it seems creepy to polynomials of linear transformations, but we've got algebra, and if you've got algebra, you've got all that you need to actually make polynomials, and this is all fine. Everybody good? Okay. Don't forget we can't commute. right? This is an unfortunate reality, but you just can't switch the order of two linear transformations. It just doesn't work any more than composing any other kind of functions you just can't switch the order. It's not how compositions work. You can explicitly see that with these two elemental atomic linear transformations here crank it out. Here you're multiplying g times f, and now taking a derivative, product rule, two terms. Whereas on the other hand, if you take the derivative first, there's no product rule. D of f is just f prime. There's no product rule, and so you get just that. So not equal. No surprise, we already knew this, you can't commute. Here's the good news though. If you have constant coefficients, constant coefficient means that this g, the things that we're multiplying by, they are constants. If they are constants, their derivatives are 0. That term goes away, and therefore these things are equal. So, neat fact, when you're doing algebra of linear differential operators, it doesn't commute, but if you're doing algebra of constant coefficient linear differential operators, you can switch the order, it does commute. So not only do we have algebra, but we have algebra with commutativity. Okay, and this is most of the tools that we need to start doing stuff. I want to do one thing with it before in the remaining 5 minutes that we have here. Make a quick observation that in the same way that you can factor a regular old high school polynomial, right? Yawn, we've factored polynomials many times. That's just factoring. Well, you can do the same thing with L. After all, L is P. It's just P of D instead of P of lambda. But this is just L equals P of D. Let me write that down. This is P of D, so that is just D's instead of lambdas, so that is just D's instead of lambdas. Then check out this observation. Well, before I get to that, let me pose a question. Do y'all remember the very first thing that we did when we were looking at homogeneous constant coefficient equations? The very first thing that we did is we said, okay, we've got no idea how to solve these differential equations. Let's try something. Maybe we'll get lucky. Let's try exponentials. Right? We pulled that out of thin air with no motivation, and I plugged in exponentials, e to the lambda x, and then you plug in and you kind of do a little calculation and you realize, oh my God, if lambda is a root of the characteristic polynomial, this works, right? So, dumb luck, we guessed, and it happened to be that we guessed right. Okay, so that's what happened way long ago. Now I want to ask the following critical question. Okay, no fair. You can't just go around expecting that we're just going to constantly guess the right answers to questions, right? So why did we guess exponentials? Why didn't we guess cosecants and square root of arctan and stuff like that? Why? What was it about exponentials? Who thought to guess exponentials? I'm going to show you I think a very cool motivation for why exponentials are a very reasonable thing to guess. And it goes like this. L, previously thought to be a mysterious black box. We now can write it in terms of algebra. We've manipulated it with algebra. We've written it as a product of what you might call linear factors of these linear transformations. And having done so, right, I can further manipulate and move factors around. So, whichever factor I might be interested in, let's say maybe this factor here of d minus r1. Let me just, maybe move that over there. Whatever, it doesn't matter. Pick any factor you like. It doesn't matter. You can move these factors around. They commute, after all. Whatever else is left over, all the rest of this junk is some great big polynomial of d. I don't really care what it is. Let's just call it q. and get it out of the way over on the left. Now, having done that, I argue cleverly as follows. If I want to make this whole thing equal to 0, here's an easy way to do it. A clever, easy way to make this whole thing 0 would be to make this 0. Right? I mean, right? If that's 0, then what does this linear transformation do to 0? Well, it would give me 0, of course. So it would stand to reason that instead of trying to find solutions out of nowhere, I should try to solve this first-order differential equation. And whatever I get from that first-order differential equation, if it satisfies that, then it should make this thing 0, which means it should satisfy my great, big, huge nth-order differential equation. And how do we solve this differential equation? Well, just rewrite it. It's a natural growth equation. We already know how to solve that. It's an exponential. So, I mean, that falls right in your lap. As soon as you have the algebra of linear transformations, as soon as you see that L can be sort of, you can take it apart. You can see what's inside of it and makes it tick. This is an immediate sort of motivation for why exponentials ought to work. Okay, we're going to do much more with this stuff after break. Y'all have a great spring break. Try to stay healthy. See you later. Have fun. Yeah.